Okay, good afternoon. Welcome to Physics 2820, Lecture 8. Today we're going to continue to talk about oscillators, but specifically pendulums as a form of an oscillator. So what I've got is a Jupyter notebook, as I usually do. If you're able to log into the server and follow along, we'll start by importing the packages that we need, as we've done every time. And what I want to talk about is pendulums. So pendulums are mechanical systems that involve some bob or mass at the end of a rigid length or rod. The mass is typically of mass m, the rod is of length L, and we usually ignore the mass of the rod itself for what's called a simple pendulum, though you could do this for a physical pendulum and include the mass of the rod. And in the simplest case, you assume that the rod swings back and forth with no friction. If the bob is pulled to one side from its equilibrium, it will begin to swing back and forth. Now, in terms of the equations of motion for this, what we're doing is not dealing with linear motion, we're dealing with circular motion. That is angular velocity and angular acceleration given by d theta dt and the second derivative of theta dt. You convert those into their linear equivalents by writing the angle in terms of radians and then using this formulation about arc length. Just to remind you how that all works, let me see if I can get a drawing tool. Right, the basic idea here is if you've got some sort of circle, some sort of arc, right? And there's the bob, and we want it to sort of swing in this sort of direction. If I know how long the rate is, and I'm talking about some angle right here, this length, which we typically call the arc length, is related to it by how far you're going. So if you want to deal with the velocity, that is the rate of change along this path, you're dealing with an equation like that, or its second derivative. It relates angles to arc lengths all the way through. If we want to do a Newton's law type formulation on this problem, what we need to do is work out the forces involved in such a problem. So we can write them down pretty quickly like this, just to sketch out what I mean by that and where this is coming from. Again, if you have a rod and a mass, there's of course one force acting on this thing, namely the force of gravity. However, you have to split it into components, right? We split it into components because the motion is constrained to be on this path. So we split it into a component which is at right angles to the motion and the direction of the motion. This motion right here is exactly balanced by the tension on the rod. It's not involved in the movement, and it's only this component right here that's involved in making a pendulum swing back and forth. If you work out the components involved, so if this is theta, and you do the thing with the triangles and you figure out the components, then this component right here will be of length, mg sine theta. That is proportional to the sine of the angle because of the triangles. And so we're able to say, Newton's second law, mass times acceleration, again, this is a linear acceleration written in terms of the angular displacement, is equal to the net force acting in that direction. That's the only force involved in the simple pendulum. The m's cancel, and you are left with this equation of motion. So this is the equation of motion for a simple pendulum. Now the thing is with this equation, and if you remember doing this in first year physics, we only solve this problem for where the angle is small. This is a solution something we can come up with an analytical solution for if we assume the angle is small. So what we're talking about here is if this is the normal pendulum, I'm solving a situation where it could be as big as here or as big as here. I am definitely not solving the situation where the pendulum starts off here with respect to the vertical. So this is yeah, and we're not doing this one. The idea of the small angle approximation is we're assuming that the angle, which of course is this angle right here, is sort of in there, is smaller than 1 everywhere, so that you can always write the sine of the angle is equal to itself. This is just the Taylor series approximation associated with doing a linear expansion of sine, which is a very complicated way of saying, if I begin to draw out a function for you and I call this function sine, here's my sine function, so y equals sine of x. The point is, as long as x is small, this line is approximated by the line y equals x, as long as x is relatively small. So that's what we mean by the small angle approximation. You can estimate sine of any small angle as just being equal to itself, where you always have to measure that angle in radians. So this is the small angle formula. And the thing we're going to observe about this pendulum motion is it has the same equation of motion, or the same formulation mathematically, as our spring mass problem did. It's an acceleration is proportional to the negative of a displacement. And that's exactly the same thing as we had with the spring mass system. Acceleration is proportional to the negative of the displacement of the system. And because of that, it has to have the same dynamics and the same mathematical properties. In particular, we know how to get the period out of this structure. We look at its frequency, and of course we can recognize the frequency squared is k over m. That means the frequency of a pendulum is g over L. If we know its frequency, we can take the reciprocal and multiply by 2 pi, and that gives you the period. So directly from the equation of motion, we're able to read off what the period is. And this is something we covered in first year physics. The idea is it's all based upon what this constant of proportionality is. Right here, the square of the natural frequency of the oscillator is given by that combination of physical constants, and that allows us to get the period right away. Now, if we want to solve the original problem, that is the equation of motion for a non-linear ODE. So we call this one down here, the second one, a linear DE, because the position, the force depends on the angle linearly. We call this one a non-linear DE because the force depends upon a non-linear function of the angle. So this is a non-linear DE. This is not something we're able to solve with pen and paper or blackboard and chalk. So what we can do is we can solve this numerically. One of the checks we can do when we're solving a problem numerically is we know that physics still has to be respected. It has to be consistent with the conservation of energy. And so we're going to want to make sure we've got an expression for the energy of a pendulum to be able to check that we're doing our numerical simulation correctly. Energy, mechanical energy, can be divided into two parts. It can be divided into potential energy and kinetic energy. The potential energy is due to how far the bob or the mass has been raised off the ground. Again, if I've got a bob right here, and let me draw this thing as a little circle right here. There's my mass sitting a certain height above the bottom. The height we're interested in here is the height relative to its sort of base state. If you can imagine drawing in what this pendulum would look like, sort of when it was resting below, right? So that's where it would be in its equilibrium position. It's raised a height up. Well, that height it's being raised is a height h. mgh is the potential energy of a system. Again, if you take this and you do the triangles, so you think about this line, you think about how long this L is, you think about this theta right here, you're able to write the h in terms of the L and the theta all the way through. And so we can rewrite that h as L times 1 minus cosine of theta. And so we get that the potential energy is mg times L 1 minus cosine of theta. So this is the kind of things we can do in mechanics, come up with mechanical energy. Likewise, a kinetic energy is written as 1/2 mv squared. In this case, the tangential velocity, the linear velocity, is L times the rate of change of the angle. We square that and we instantly get a kinetic energy. All together, we're able to put these things and come up with an expression, which might look a little bit different, but it's just an expression for the total energy of a pendulum. So that's the modeling. That's sort of the mathematical stuff. This kind of modeling is well within the ability of everyone in this class. I'd encourage you to go through with pen and paper and just try and reproduce these results. I'm expecting you can derive these kind of things from first principles doing some geometry or algebra to figure them out. Okay, on to the numerical solution. What I'm going to do is follow the same structure we've been doing and write an application, and I'm going to call this a simple pendulum application that implements a numerical stepper that solves the following dynamical equation. The dynamical equation is the second derivative of the displacement angle is proportional to the sine of the angle. As we've done before, we can split this up into two first-order differential equations where we're very specific. We talk about this part inside here. This is sort of the angular velocity. So it's the rate of change of the angular velocity equals, well, this is really the angular acceleration. And then you have another differential equation that says the rate of change of the angular displacement is the angular velocity. You get two equations, same thing as we've done before. The natural frequency of the system is going to be given by the square root of the thing that's in front of it. This is true even if it's simple harmonic motion or just a more generic kind of oscillatory motion. And what I'm going to do in this problem is, rather than talking about G and L explicitly, what I'll do is I will choose L so that I get a particular value for the natural frequency of the system. So one way of doing that is say that what I wanted was I wanted a natural frequency of 3. I may want to have this vibrate at a natural frequency of 3 radians per second. Well, 3 squared on the bottom divided by G, basically rearranging this formula, I'm able to solve this thing for the L that is needed to give me a natural frequency of omega naught equals 3. We probably won't need the mass anywhere, but just in case we do, the mass of the pendulum does not appear to be important, but I'll just give it a hard-coded constant in case we ever need to bring in that variable somewhere else. Okay, what I'm going to do is use the same code we did last time, a simple harmonic motion, and I'm going to adapt it. And rather than having to go through and change all of my x's to thetas and my v's to something else, I could just keep on using those things as long as I'm clear on what the variables mean. So in the code below, what I'm going to do is I'm still going to talk about the variable, I'm going to talk about the variable x, and I'm still going to talk about the variable v, but now we're going to interpret those variables as being the displacement and the angular velocity. So angular displacement, angular velocity. Still using the symbols of x and v because it doesn't really matter what we mean. It's something to do with the position, something to do with the velocity. So there's no need to go through and change it necessarily, but it is helpful to indicate somewhere in the text what you're doing. The only real difference between this and the code that we did for the simple harmonic motion is the statement of the acceleration. In the simple harmonic oscillator, the acceleration had this form. Okay, for a simple harmonic motion, Hooke's law, that is a spring force, the spring pulls back at a force proportional to the displacement. In a pendulum, it swings back with a force that's proportional to the sine of the angle. So that's the only real difference, and of course the constants change. So if you take a look at the actual code, and we'll use the Euler-Richardson model to solve this. It's got the same basic setup. We initialize our model. We're going to stop when we've reached a maximum time of Tmax. And I'm going to use an acceleration of g over L times the sine of x. Now, all our mathematical functions come in NumPy, so that's why the NP is there. And if we're doing the Euler-Richardson method, so this is a little more complicated than just basic Euler. The idea is we're going to estimate what the acceleration is and the velocity is at halfway through the interval, as we talked about last week. So the idea of this numerical scheme is start by estimating the acceleration at the old position, use that acceleration to come up with a new guess for the velocity halfway through a current interval, and then use these new middle values for velocity and position to estimate again the acceleration in the middle. So if you notice what I'm doing here, I'm calculating the acceleration at the beginning of the interval, that is the old x, then calculating at the midpoint and using that to update the acceleration, update the velocity. And I use this midpoint for velocity to update the displacement. That's the Richardson-Euler, Euler-Richardson algorithm. But the only change we're making between this and the simple harmonic motion stepper code is to change the force all the way through. Okay. We need a way of plotting the results. So the simplest thing to do is to plot the vertical and horizontal components. Just for the purposes of pedagogy, I'm just going to comment out those two lines about the analytical solution. What I'm going to do is I'm going to make a plot. It's going to have three parts. I'm going to plot the angular displacement. I'm going to plot the angular velocity. And then the third plot, I'm going to make a plot about the energy because I want to see whether or not my numerical solution is stable. To plot this, and there's a lot of extra code in here, but I'll focus on the important bits. We're passing in the results of our stepper, something we've iterated through. I'm going to plot in the top block, X on the horizontal, on the vertical, T on the horizontal, and give it a label. In the middle block, I'm going to plot V versus T. And then I'm going to calculate the energy, as we've done before. Calculate the kinetic energy, calculate the potential energy, and put them all together. So that function with a stepper and a plotter, something to visualize, it allows us to write a nice little application. Let's set this thing up with an initial displacement of 0.2 radians, set it swinging back and forth with a time stepper of 0.05. And the idea of all of these models is you got to set up the model, actually run the model, and then you'll look at the output all the way through. Now, simple pendulum stepper is not defined. That probably means I just missed something. There we go. G is not defined. I missed something else. Always run all of your cells. Let's try again. There we go. Now, one of the things about this code is you'll notice that at the end of the code, I return the data. I'm going to return the data because I may want to actually look at the numerical values all the way through here. If I get rid of that semicolon, then it will spit those out when I return the program. If I want to hide that, a nice trick in Jupyter is to put a semicolon at the end of a line that will prevent Jupyter from displaying the last result inside of a cell. There is a question I got in the chat. How is this way different than making dt half of its values? In both cases, we make the calculation as more accurate. That's true. You make it more accurate. It's the way in which you're making it more accurate. In an Euler method, by reducing dt by a factor of 2, you make it more accurate proportional to the size of dt. Using this Euler-Richardson method, you make it more accurate proportional to the square of dt. That is, if you reduce dt by a factor of 2 in the Euler method, you reduce your error by a factor of 2. With Euler-Richardson, reducing dt by a factor of 2 reduces your error by a factor of 4, 2 squared. So it's a second order method. So it's better, but it's much better for Euler-Richardson. And there are third order, fourth order, and fifth order methods as well. Okay. So what this app is doing is it's showing a numerical response, and what you're seeing is the pendulum moving back and forth. It starts off at an angle towards its right. It gets pushed towards equilibrium. As it gets pushed towards equilibrium, it's going to speed up. That's why you see the velocity going negative here. Right here, you have no displacement, so there's no change in velocity because there's no acceleration. And then, of course, as it passes through here, it begins to pull away from equilibrium. So there's a net force that causes it to accelerate back towards equilibrium, and the pattern returns. One of the things you can see is if we plot the kinetic energy, potential energy, like in lots of oscillators, there's this exchange going on between kinetic energy and potential energy, but the total energy is remaining flat all the way through. Okay, so let's do some things with this code. Let's make some changes so the analytical solution is also plotted so we can experiment with this. And I've already done this. I'm just going to work through this. The basic idea of the small angle solution is to look at what a pendulum would do if the angle was small and try and figure out what that analytical expression would be. Now, if you sit down with pen and paper and we start with this equation up here. One of the things you may recall is you can write down the system of any linear oscillator in terms of sine and cosine functions. If the x component is a sine, then the y component is going to be a cos and vice versa, or a minus cos and minus sine, right? Because they're derivatives of each other. Depending on what the initial conditions are, is going to tell you whether or not one is a sine and one is a cos, or vice versa. So if you actually go through it in pen and paper and you try and figure out what these equations should be, I think it's fairly quick to figure out that for an oscillator which starts at an initial displacement, some angle, with no initial velocity, that will be its analytical solution. So all we're saying is it's going to swing back and forth and back and forth. That's what's represented by this guy right here. It's swinging back and forth at a frequency given by omega naught. I'm specifying omega naught. It's going to start at its maximum, which is why I'm using a cosine, and it's going to swing back and forth and back and forth. To figure out this next line, where does that come from analytically? It's just the derivative. If you take the derivative of theta with respect to t, take the derivative of cosine, you get minus sine, the derivative of omega times t, the omega comes out. So this becomes the analytical expression for the angular velocity of a pendulum. Okay, so all of that is to say, what we're able to do is add in the analytical solution. The only one piece of information I need is I do need to know what the initial velocity is. These data things are pandas data frames. I can take the first row and grab the x value, and I would have it all the way through. You could do this more substantially, where you work out what the initial angular velocity was and extend this so that it works for any angular velocity in any initial position, but I've done it assuming the initial angular velocity is always 0. Just evaluating an amplitude times a cosine times a frequency times time all the way through. Okay, well, let's add those curves, those plots all the way through to our solution. I'm just going to plot on the same graph the analytical solution and the position all the way through. Rerun that block, and you'll see two curves now. The curves are hidden because the blue line and the orange line are very close to each other. The difference between the numerical and the analytical solution will appear if either I'm using a nonlinear pendulum or I've chosen a poor value for my time step. So a nice thing that we can do is use these interactive blocks to explore the effect of A, initial angle, and B, time step. So we'll start here. This is where it was before. This is sort of the initial case. First thing I want to draw your attention to is time step. Any numerical model, the time step needs to be checked. In particular, take a look at what happens if I chose the wrong time step, if I made bigger steps in time. As I make bigger steps in time, I hope you can notice a couple things. One is the numerical and analytical solutions are no longer the same. That's a hint that we've done something incorrect. The reason we've done something incorrect is because the energy in the system is growing over time. Euler-Richardson is better than Euler, but it still suffers from a similar problem that if you have too large a time step, as defined as the acceleration is changing over the period too quickly, then it's not going to work out. You're going to have an unstable solution. And in fact, if you crank this up and you started with an artificially high value, your growing energy is growing quadratically in time. We have to make sure that the time step is small enough. I think as I look through this, using the green line has to be flat. 0.1 is not bad. It's not great. If we drop it down to 0.05, that line's looking pretty flat. If you wanted to use 0.01, that'd be good too. That's the first check. The second thing we can investigate is how a simple pendulum differs from a simple harmonic oscillator. If the angle is small, these two curves, the blue one and the orange one, line up perfectly. But if the angles start to become big, so initial radians of 0.5, 0.6, 0.7, 0.8, 0.9, 1. Just for understanding, right? Because radians are something we don't always work in. If I give you a circle, right? A circle The entire circle has 2 pi radians, which, as everyone knows, 2 pi is basically 6. So that's all the way around the circle. So a angular displacement of 1 is 1/6 of this. It's basically the situation. That would be a radian of 1 approximately relative to the whole circle. You have a pendulum swinging back and forth. The small angular solution approximation is actually going to start to fail. The analytical solution, the red one, is now wrong. The blue line, our numerical solution, is more accurate because it includes more advanced physics. It includes the fact that since you're not making the small angular formula and approximation, the blue line is actually what this pendulum should go and do. I don't know if you ever did an experiment like this in high school where you had to figure out the amplitude of a pendulum, and you watch it and you count the oscillations back and forth and back and forth. But one of the things you'll notice is for a true pendulum at non-trivial angles of displacement, the period is actually a little bit longer. That is the distance in time between when the system gets back to the same point again. It's actually stretched out. It's got a larger period than you would expect for a linear pendulum, one where the angle was small all the way through. Okay, so we're able to do that kind of analysis with these kind of codes. Part 2, test the program at sufficiently small angles so that the small angle formula is valid. Okay, we did that. So you'd want to always test your program at a small angle to make sure that they matched up exactly. That means you've implemented the code without any errors. What else do I got to do? Determine the period numerically and compare your result to the expected analytical result for small amplitudes. Explain your method for determining the period. Estimate the error due to the small angle approximation. So this is a problem I've just taken out of the textbook, but we can do it together. The idea here is I need some way of measuring what the period of these things are. There are a lot of methods for measuring the period of repeating things, but I'm going to use a fairly simple method. I'm just going to look at where the maximums of this curve are and then look at the difference between where those maximums happen to be. So the idea here is I'm going to write a function that figures out the period of this data. This is why I was always making sure that my function returned data so that I could use it. I talked before that if I ran the program by itself, it would do 2 things. It would spit out all of the data and spit out the plot. If you want to hide the data, you either could put a semicolon in there so that the data doesn't get printed out, or capture it in a variable. If you don't want the plot to be shown, close the plot before it has a chance to be printed, and you get no plot. So if you ever want to get rid of the plot before showing it, click .close. Okay, let's take a look at this data. What the stepper is giving back after you iterate through it is 3 columns: the current time, the current position, and the current velocity. Head is just a way of saying, give me the first so many rows of a data set. If I ask for 10 rows, I get the first 10 rows. There are more rows than this, right? The whole thing goes down, and it actually is 201 rows. But I don't want to look at 201 rows, so I'm selective on what I want to look at. I only want to look at the beginning. What I want to do is I want to write some code that figures out where the peaks are in this program all the way through. I want to figure out where these peaks are, namely where X is bigger than left and right. And so here is a code that does it. Now the thing with this code is it's pretty dense. It's got a lot of lines in it. So I want to break it down into pieces so we can go back to it and take a look at it. The first thing is I can talk about the data in the X column all the way through. And I can use this column to figure out where the maximum points are. That is the points, any point X, which is bigger than the point to the left of it or the point to the right of it. If it's bigger than the point to the left and the point to the right, that means that X must be a local maximum. That's what this fairly complicated line is supposed to be doing, but I'll break it up into pieces by evaluating all of the different parts of it and putting those parts into a data frame. Let's quickly just run it, and then I'll go back. This thing is made up of a number of different pieces. It's made up of the data X, that is this column all the way through. And I'm representing that right here. If you can see, we've got a column. These are a bunch of different points in X. I can take that column and I can shift it forward. That's what shift 1 does. If you notice the 192, 192, 198, 198, 200, 200, that column's just been shifted forward. You can also shift the data backwards by 1. Take that data and shift it up. The 198 becomes the 198, the 200 becomes the 200. And then we can ask a question. We can say for every one of the elements in this row, what I want to do is compare them. I want to say whether or not the shifted data is smaller than the original value. So for every one of these values, I'm comparing this one to this one and asking, is this value bigger than the one before, the value to its left? Is this value bigger than the one to the right? And it is bigger than the one to the right, but it is not bigger than the one to the left. If you're on the other side of the maximum, this is smaller than this one, but it is bigger than this one, which is why you get a false and then a true. For it to be a maximum, you need that operator right there. That's a logical and. It says if this thing is true and this thing is true, then they both are true. So by logic, if true and true are both true, then the whole thing is true. All that is to say, I'm trying to figure out a single condition that tells me where my maximum is. It's only the situation where this number is bigger than the one before it and after it. That's a maximum. It gets a true. And then what I do is only for the values which are true, I copy those into an array called data max. That's all this is doing. It's a fancy way of identifying where the maxes are all the way through. Okay, so after this has all been gone through as a piece of logic, what's the next thing I do with my program? I take that new table, and you see how there's a bunch of NaNs. That stands for not a number. Now I could look at the entire table. I could look at the first 45 rows, okay? It's a pretty boring table. Most of the rows have not a number because those are not maxes anywhere in the program. So what I can do is I can use a pandas feature to drop all the not a things, not an infinity, not a numbers, just drop anything that's not a number. And that gets rid of all the lines in this table, this 200 line table, where there are any not a numbers, NaN, not a number, all the way through. If I'm figuring out where the period is, what I'm really interested in is what the coordinates t are all the way through here. So I can take this column, which is the t column, and I can say, okay, you know what? What I really want is I want all of the t values all the way through. I want the 2.1, the 4.2, the 6.3, and the 8.3. Finally, if I want to figure out the period is just the difference between the successive values of these diffs. Think about a function that's oscillating up and down and up and down. If I know this coordinate and this coordinate and this coordinate, if I take the pairwise difference, that will be the period of this cycle. So we do that. We use the difference. What that does is it takes the difference of every pairwise operator, and I get some numbers. Now the first one doesn't work because the first pair doesn't have anything before it, but the last three do. Finally, what I can do is take those numbers and calculate the mean of all of them to figure out the period of the whole thing and compare that to my analytical period. Now, they're not exactly the same, but they're at least in the right ballpark. Question on the chat. When you shift values in a data frame left and right, what happens to the first and last values? Okay, fair enough. Good question. What happens is any value that you doesn't know becomes a not a number. So if you shift 2.0 to the right, it's getting shifted, and that becomes I don't know what it is. And if we look at the last 5 values of the table, I've shifted towards the left or whatever which way you want to talk about it. I've shifted this one back. It becomes not a number. So not a number is used in pandas to represent values that I don't know. They're not zeros. They're just, I don't know what that is. I have no idea. It's not a number. Okay, all this is to explain what this function is supposed to do. But now if we look at it, we're like, oh, okay, what you're doing is finding the maximum and then computing the average period all the way through. Let's run it and see if this guy works. What we can do is we can take the data, and now I can do it all in one go. I can just say, find pendulum period of the data, and it spits back a number, and that's the period. So building a helper function like that is useful because we may want to use it again. Now let's make a plot of the period of the pendulum as a function of the amplitude. That is a function of the angle. We've already observed that when we run it interactively, as I make the initial angle, which is also going to be the amplitude, larger, the period tends to increase. I want to make a plot now where I vary this parameter along the horizontal, and I calculate or compute the period all the way through. These kind of problems, when I want to do them one versus another, we typically want to use a loop of some kind. One model is to do a for loop, that is to set the position and have it change, starting at a small value, going to a maximum value, solving the complete problem, and instead of plotting the result, I'm going to use the result saying find pendulum period, and then put an X on the map, on the graph, at that pair of points, initial angle, and the period I found. Then I can also, on that same graph, plot the angle that I'm working with. Okay, so here we go. This is what this routine gives you. You can see that as a function of initial amplitude, the period does tend to increase with amplitude. Now, there's some things that you might find a little bit odd about this. One is it tends to do this steppy sort of nature. Well, the steppy sort of nature is partly because I can't get a precision any better than the size of my time step. If you notice your time step right here is 0.05, that means that I can't talk about hundredths of seconds. The best I can do is talk about 20ths of seconds, 0.05. So that steppiness is not too crazy. If you had even a bigger one, there's some other errors that are coming through. I'm talking about those in a second. So the first thing you want to do probably is shrink this time step down fairly good. Now, it's still not perfect. And the reason it's not perfect, again, has to do with how I'm actually figuring out what the maximums are. This particular routine is estimating the maximum at the location of X, which is the largest in this set. That doesn't mean it's the true mathematical maximum. If I give you 3 points and I say, go through here, here, and here, this may not actually be the true mathematical maximum because there's a bunch of points that we don't know. There's the values of X in between here and the values of T in between here. The maximum could be somewhere else in that interval. It's near 0.02, but it may not be exactly that. One way of overcoming this is to use many measurements of the period for lots and lots of different times and averaging out over them. So if we run this not for just 10 periods of time, but for 20 periods of time, or 30 periods of time, or 40 periods of time, what I'm getting is the average period of a whole bunch of different oscillations. It's equivalent to running this model and just running it not just for 1, 2, 3, 4, but running it for, say, 40 oscillations. The more oscillations you have, the easier it is to estimate the period. And here's something really nice about estimating periods. Even if we had a poor choice of time step, okay, that doesn't look so pretty. I actually can run my model for longer, and just by running it longer, because I'm averaging over more coarse estimates of what the period is, I'm able to get a nice, smooth representation all the way through. So there's sometimes you can just run the model for longer and do averaging to overcome these kind of errors. There's a bunch of tricks. Of course, I probably want the best of both worlds. I want the most precision I can get and the least error in that period. So that's the graph of how the period depends upon the amplitude. So qualitatively, period increases, looks to be sort of quadratically with the amplitude. For small amplitudes, you wouldn't notice, but it does slow down all the way through. Okay, let's keep on going here. Is there any more questions in this thing? Right, okay. So this is the question of the book, and everything I've been talking about was just the answer to that question. Motivates the lecture. Okay. Okay, so that's a nonlinear pendulum. Nonlinear pendulums depend, their size of the displacement matters all the way through. Is there any questions about the nonlinear pendulum? No one's putting up their hand, no one's turning on their mic. Okay, let's continue to explore. Let's look at a damped harmonic oscillator. Oh, Kayla raised her hand. Awesome. Do you have a microphone, Kayla? Or are you typing?
Can you hear me?
Hello there, Kayla.
Hello. I just wanted to ask or clarify, are you finding the pendulum period going back up to the location of the peak in the sinusoidal curve?
Okay, you are very quiet on your microphone. You asked something
I'm not
about...
sure. I'm just trying to, I'm not trying to speak loudly. That's probably. I'm not sure.
You're not sure about...
Oh no, I'm not sure. I'm from quiet. I feel like I'm from quiet in the mic, so I was saying I'm not sure why.
Okay, well, we'll have to try that again a different way. Maybe Kyle can answer your question one-on-one. I think that might be the best way of proceeding.
Oh, okay.
Okay. Okay, sorry about that. Okay, we'll continue on. So the next thing we want to attempt is looking at an oscillator when we add in damping. A real pendulum does not swing forever. Eventually it comes to rest. The reason is there is dissipation in the system. There's a loss of energy all the way through. To add some damping to our model, what we want to do is include the effects of friction. Friction, like an air drag, is proportional to the negative of the velocity in the system. The faster the system is moving, the more friction there's going to be. If the system isn't moving, there is no friction for these oscillating sort of systems. One way of modeling this is with a damping coefficient. The textbook uses the variable gamma, sounds like a reasonable letter. So let's do that and add in a damping coefficient to our equations of motion. What I'm doing is I'm adding in a new force, a drag coefficient right here on the right. I'm saying that the acceleration is due to the restoring force plus this additional force due to the damping. Okay. Now, studying an equation very similar to this is something that's the topic of a mathematics course in ordinary differential equations. If you have taken, and you do not need to have taken, you might have taken, it does not matter for this course at all, but you might have taken a course in ODEs, math something, that had equations of this form. That is a second order constant coefficient differential equation. That kind of equation is what we study in the analytical methods in a typical ODEs course. And the trick is this is a constant and this is a constant. Now, we are not assuming in this course you've done differential equations. You know how to solve this equation. There's no need because what we've learned is how to solve these problems numerically. So let's take our oscillator, our pendulum problem, and add in damping to see how the behavior changes. Okay, I have a damped pendulum stepper. It's basically exactly the same code where I want to do just a few small changes. Change the comet, so it's clear what this code is doing, and I want to add in a force. Again, the way that Euler-Richardson works is you evaluate the acceleration first at the starting point of an interval, that is the value of x and v at the old value, and then you estimate it again at the midpoint of the interval. So imagine you're going from an old value of x to new value of x, from old value of t to new value of t. V mid, x mid, and a mid are the midpoints halfway through. And halfway through, we estimate not only the restoring force halfway through, but the drag force or the friction force halfway through. That's what the purpose of these mids are. So we have to evaluate it twice. But other than that, it's exactly the same code, which we can then go and run. And we can do a plot. This plot is exactly the same plot. I've just removed the analytical expression because it doesn't apply for a damped solution, or I'm not going to include it. And here's a plot that does two things. It's going to plot once for an undamped pendulum, that is one where gamma is equal to 0. This is what we had before. And the second plot is going to be gamma equals gamma. I guess I have to run it. There we go. We have to run it all the way through. There we go. Perfect. Okay. Oh, I left those in. I thought I'd taken those out. We'll take those out in a second. So what do we got? We've got two models. We've got an undamped situation. This is what we were dealing with before. And then we have a damped situation, this orange line. And you can see that it's decaying in time all the way through. Why is it decaying? Because every time it goes through the operations, you can see that its kinetic and potential energy are getting smaller and smaller and smaller and smaller. The dashed lines are the kinetic and potential energy. The solid lines are the total energy of the system. Something about the code here, because it might throw you off. You know, we've been using this idea of subplots. Well, here's a situation where I want two different sets of data to appear on the same graph. I want them to appear all together. I don't want to show this graph and then beneath it show another graph. I want all the data to show on the same page. So one technique we can use is, rather than creating the plots inside of the plotter, I can create them outside of the plotter and pass them in as an argument as well. So the idea here is I create the axes, the actual plot I'm going to put the data into on the outside, and I pass them in so I can make them work. I set this as a none. What that means is, by default, it'll be equal to a null value called a none in Python, and I can test for that. And I can say, well, if you didn't give me an axes, I have to create my own. But if you did give me some axes, then I can proceed to use them. So it's a way of reusing axes all the way through. Okay, let's answer some questions about this model and see if we can understand a bit more about damped pendulums all the way through. So here's some questions. I want to make sure I talk about qualitative effects. Okay, so that's pretty straightforward. As you damp a system, it's going to decay all the way through. The reason it's decaying is because the energy is being taken away, because there's a net frictional force. That's not a conservative force. Friction forces are not conservative all the way through. If you play with this code and you increase the amount of damping that goes on, I think what you can see is it damps faster, right? It really takes all the energy out of it. And if I put in a very, very small amount of damping, okay, a damping factor of 0.2, it damps fairly slowly all the way through. Okay, so that's the basic idea of damping. The period is the time between successive maximums of displacement. What happens to the period? What does damping increase or decrease the period? So let's play with this. Okay, so here's some damping. Let's put some moderate damping on here. We want to sort of see the oscillations. Okay, so bump, bump, bump. The question is the period between the blue and the orange, are they changing? Well, as I increase the period, we know that the period of the whole thing will stretch. But what we're trying to figure out now is whether or not the peaks here and here, and specifically the distance between the peaks, are those changing between the undamped and the damped case. I don't know about you, but I find this interactive way, it doesn't tell me it right away. I'd really like a better control and see what the period is on a graph. So we do that. Let's write ourselves a brand new application that explores what a damped pendulum period would be, exactly the way we did before. And as before, it was a loop, go through a whole bunch of different initial positions, call my damped stepper, and take a look at what you're going to get, a bunch of x's, and then plot the analytical solution for reference. Okay. Well, that's sort of interesting. So here's the period of the system. This blue line is what it would be for an undamped, not linear PDE. If I bring the damping all the way down to 0, I get the graph that we had before, right? Increases all the way through. If I add some damping into the model, I want you to see that for small values of damping, it doesn't change too much. But for moderate values of damping, it appears that the period, even for small amplitudes, actually starts to go up. And there's another effect. As you increase the damping, as you make the damping higher and higher, the dependence of this amplitude, of this period, on the initial period starts to go away. Once you get sufficiently large in your damping, the period becomes independent of the starting amplitude. This is a characteristic of a lot of oscillatory systems. There's an initial transient. What happens at the very beginning of the motion, that is where it starts. Does it start at equilibrium? Does it start above equilibrium? That changes things a little bit. But after a while, it didn't really matter where it started. It doesn't matter if a pendulum starts off at rest and you give it a kick, or you start it off displaced from equilibrium and you let it go, or any combination of the two. Eventually, the period will settle into something which forgets about what that initial displacement happened to be. So we can see here is for larger values of damping, that number is completely independent of the starting initial angle. However, as you increase the damping, let's take a look at the numbers here, 2.18, 2.20, going up a bit further, jump up a bit more, 2.27. So it's moving up irrespective of the amplitude. So that suggests that for this kind of plot, we really don't want to plot period versus amplitude. We really want to plot period versus gamma. So let's flip it around. Let's take this program, and you see I've called it damp pendulum period 1. Let's call it damp pendulum period app 2. And the only difference is now what I'm doing is I am looking at how gamma changes all the way through. Depending on how many people are running. So here we go. What we see is, relative to an analytic solution with no damping, the period itself depends upon the damping. So now we have two dependencies on the damping. One is, for an undamped system, there's an effect due to an initial angle. For a damped signal, that effect is small and gets progressively weaker as the damping increases. A damped system has a larger period than its natural frequency. What this means is if you have a system that's oscillating and you measure the frequency, if there's damping in it, the frequency you measure is not the same as the natural frequency. The natural frequency for a pendulum, square root of G over L, is not the same as the frequency or the period you'd actually measure in a real system. For any real pendulum with damping, that is, it's slowing down as all real pendulums do, the damping period that you measure will always be larger than the natural frequency or the true frequency of the system or analytical representation. Okay, what else can I talk about in terms of these things? Total energy is a function of time. Is it decreasing monotonically? Explain. Okay, so here we go. Here's this graph. And you can sort of see what's going on is every time it decreases and then stops decreasing, decreases and stops decreasing, decreases and stops decreasing. It's always going down, but there are moments where it actually becomes flat. Those are the moments when there's no velocity. If you look right here, right here, right here, those are the moments when the pendulum is at its extremes, either furthest to the left or furthest to the right. It's not moving. If it's not moving, then there's no friction. If there's no friction, there's no loss in energy. So the energy is lost whenever the pendulum is swinging. It's not lost continuously. It's lost whenever it's moving, it loses energy, and then it stops moving. And it starts moving, it loses energy, stops moving. And it starts losing energy, it stops moving. So it's decreasing, but it's not decreasing strictly monotonically, as in derivatives are always negative all the way through, because the energy loss is dependent upon the velocity. Okay, and now we can do some playing around. Let's investigate the dependence for a range of these damping parameters. Let's take a look at what happens to these graphs as I vary the damping parameter gamma. Well, first thing is this parameter right here is actually not overly important anymore. What we've discussed is once you are away from an initial condition, it doesn't really matter what you set this to understand the behavior of it. All it's going to do is set the initial height, the amount of energy in the system. But the actual picture is the same. You see that? Starts off at 3, starts off at 0.5. It changes the energy, but it doesn't change the shape. What does matter, though, is the amount of damping. If I add in more damping, then what you can see is the energy drops off even faster. When a system undergoes these oscillations, we call that an underdamped situation. If you crank up the damping a lot, so that it just drops off, we call that an overdamped situation. There's a special amount of damping that if you set the damping just right, let me see if I can find it here, where the system does not bounce at all. What I'm looking at is looking at right here. I put my eye on it so you can see what I'm saying. No, not that, not that, not that. I'm looking right in there is where my eye is drawn to. If I increase the damping, there is a point at which there's no bounce at all. The system basically goes from equilibrium and it's slowing down just at the right rate so that when it hits the equilibrium point, it stops. That scenario is called critically damped. So this is the one where the time it takes to get to the equilibrium is exactly the amount of time needed for all of the energy to leave the system. That's an example of being critically damped. Underdamped, right, subcritical, you don't have enough damping, so there's still a few oscillations all the way through. If you overdamp the system, then what happens is the velocities here, let's crank this up so I can get a bigger number. I'm going to change this to 20. That's just the maximum damping. If I change this damping so that I really damp it a lot, you'll notice that the damping is so much that the velocity gets to 0 almost right away. Remember that the damping is affecting the velocity. If the velocity is positive, it starts to damp right away. But it's still away from equilibrium. Because it's equilibrium, even though it's not moving, there still is a restoring force trying to drag it back. So it'll very slowly tend to drift towards equilibrium. So if you underdamp a system, it's going to bounce around the equilibrium. If you overdamp a system, it's going to drag and sort of stop. If you want it to just be perfect, then you want to critically damp it. I can imagine the scenario of, you know, those spring doors or the doors that are in front, the sort of the thin door in front of the main door. Typically, it's got some covering in front of it. It might have one of those gas cylinders that it causes it to close. You can imagine controlling the damping on that and doing it badly. One way of doing it badly is if your door does the equivalent of this, right? You can imagine someone building a door with a gas cylinder damper on it, and it swings back and forth and back and forth and back and forth, or your car shocks bunching up. That's bad. But almost as bad is this scenario where you overdamp the system, and then you got one of those doors that closes so terribly slowly. I don't like those doors. I like my doors critically damped. I like them right there where they're just closing just the right rate so that they just close until they're done. It's like one swing, critically damped. Okay, so all that is just an aside, but about oscillating systems all the way through. Let's do the last thing. The last thing I want to talk about is something called a phase diagram. So rather than plotting for these oscillatory systems, displacement as a function of time and velocity as a function of time, what you can do is you can plot the displacement and the velocity together on the same graph. The state of the model is given by its position, and its velocity that uniquely determines where the system is. It's called its state. Together, we call this thing the phase of the system. And so if you plot position versus velocity, you get something called a phase diagram. So let me show you that now. A phase diagram is plotting x versus v all the way through. So there's no time on here, or rather the time is built into the diagram. This is time equals 0. This is time equals 100. And what you're doing is you're following the model all the way along. The displacement gets more and more negative, or decreases from the right towards the left. This is the pendulum swinging from right to left, and then from left to right, and right to left, and left to right. And this direction is the velocity. It swings fastest in the first pass, and slower, slower, and slower. This point in the middle, this focus point, which happens to be the origin in this graph, is called an attractor. The system is being sucked into that attractor, and that's just, of course, the equilibrium solution, the one where the pendulum is in equilibrium. It's not moving at all. Depending on the damping parameter, we can take different trajectories in phase space to get there, all the way through. These parameters are controlling how we get there all the way through. And I talked before about how this displacement, it's important, but it's not really important. Take a look at how the initial displacement affects this phase space. Again, this dot right here, that's an initial velocity of 0, initial position of 1 radian, and these are the curves at different damping. As I shrink this down, and let's say I gave it only a little displacement, so it was only a third of a radian, the picture is exactly the same. And what this speaks to is in a damped situation, there's a certain time constant about how long a system takes to slow down. That time constant is independent of the initial condition all the way through. So this is another way of looking at these oscillatory systems. The last topic I want to talk about in terms of oscillatory systems, we talked about damped systems, we talked about nonlinear systems. The third thing is externally forced systems or driven systems. In a pendulum that's damped, if you want it to keep on swinging, think of a grandfather clock. You want the grandfather clock to keep on ticking away, swinging back and forth. You need to provide a source of energy that compensates the system for its dissipation internally. There needs to be some force or perturbation to prevent the system from coming to rest. One way of modeling such a system is to add an external force in addition to the linear restoring force and the linear damping force. For a generic simple harmonic oscillator, what we'd be looking for is an equation like this one. So for a spring mass system, the angular frequency would be the square root of k, the natural frequency would be the square root of k over m. You can still have a damping parameter. And then you need to have some term that's going to push it. And the thing about pushing it, and if you can think about like pushing a child on a swing, you don't just want to push all the time. You want to push and not push in the right period, in the right frequency. You want to have a time-dependent force. Many of the forces in nature are periodic, so we can model that time-dependent external force as a periodic force. That is to say, the equation of motion will be a second derivative of Newton's second law with a force which itself is oscillating. We say the amplitude of the force is A. It's how much the force is going up and down, how strong you're pushing. And then omega is the rate at which you're applying that force. Are you pushing quickly and slowly and slowly and quickly or not? Now, if you're doing it for a pendulum and not a spring mass system, your x's become thetas, your dxdt's become angular velocities. Strictly speaking, I guess this force becomes a torque, but it's the same basic idea that it can be modeled as an oscillatory system all the way through. Okay, so what this does is this will add energy to or take energy out of the system. And one of the things to understand about these type of externally forced systems is this frequency is different than this frequency, but now the system has two different frequencies it gets to work with. Well, this frequency modified by the damping is one, but then this frequency you're forcing it is another. And the dynamics of these things depend upon the differences and similarities between those two. Let's write a model. The only difference in this model is I need to modify my stepper so that now it also includes an external amplitude and an external frequency. So the only difference all the way through is we want to modify this thing so we've got an additional A and an additional omega. And I need to modify the force term so that I've got this, this guy built in right here. Again, this is really the acceleration of the system. That's what we're modifying. So as before, for a linear driven damped oscillator, there's your restoring force. There's your damping. And then I want to add on an external force all the way through. The thing about using a method like the Euler-Richardson method, again, is you need to calculate the acceleration at the beginning of an interval and then at the end of an interval. So for this particular case, your force depends upon your position, your velocity, and your time. So you have to evaluate all these three things. In the most general way of talking about a derivative, you might have seen us write this before. Right? There's a generic ordinary differential equation, and a lot of our differential equations have depended only on V. In general, the force can depend upon, the variable y and t in any combination. So here's a situation where the force depends upon the position, the velocity, and the time. Now, I'll make this into a vector if you want, because what we're really saying is the vector position, comma, velocity, and time. That's the most general form of a differential equation. And what we've learned is how to solve any differential equation of that form. One of the tasks that I'm hoping you're able to do is, given an equation, so if I give you, I give you this block, and I say, okay, here's the equation of motion, write down Euler's method, or write down Euler-Kromer, or write down Euler-Richardson. You can figure out what that's supposed to say. It's almost always the same. The trick, though, is knowing what to write here and what to write here, depending on the order of the method. Okay, let's run this thing and see what we get. I have a plotter. What I'm going to do is plot time and V. And now what I want to do is I want to look at both time series plots, as in x depends upon t and v depends upon t. And I want to look at a phase plot, a phase space plot of x versus v. So what I'm going to do is I'm going to put two of these lines on one plot and the other one on the second plot. We'll just keep the amplitude constant at 1 all the way through here for this demo. And here we go. Okay, lots more things going on. So let's just walk through them. What we can play with is the initial conditions of the model. I can change. Let's get rid of damping. Let's get rid of, no, we want some damping. A little bit of damping. Okay, the system starts right here. Position of angle equals 1, no velocity. It can start anywhere we like. If you wanted to start it off with lots of velocity and no position, you could start it up here. It doesn't really matter. The behavior of the system is pretty independent towards where you want to start. Okay, so these first two components are just choosing where it starts. It goes through a transient. It goes through some period where it's changing the behavior of the system, and then it goes to some cycle. And the cycle is the interplay between the external forcing and the actual system. Now, this initial bit's called the transient. We don't really care about that. What we care about is the long-term pattern. To understand the long-term pattern, we may want to run the model for a lot longer. You can see that the motion is really divided up into two parts. This is what's called the initial transient, and this is the long-term behavior, otherwise known as the steady state. The reason you're getting these oscillations is the initial position velocity is so much out of kilter with the steady state. If we were to choose a slightly different starting point, you'll notice that the transient is much weaker, not nearly the same transient. It's because when your initial state is far away from the steady state, then you're going to get this large transient all the way through. Okay, so that's the first thing. Second thing is we talked about damping. Damping is controlling the amount of time it takes to get to steady state. If there was no forcing all the way through, I don't know how I'm going to get this. I want it to be a, oh, I didn't set that up as a way of making it 0. We'll put that in there just for the purposes of demoing it. If I have no amplitude at all, then the system will reach this steady state all the way through. But if there's amplitude, if there's forcing in the system, sorry, put that back, then the system is converging towards a steady state. So again, here's where it starts, here's where it ends up. And let's run this now for not just 20 cycles, but we'll run this for 100 seconds. Can you see how there's that large line right there? It's going around and around and around and around. That's the steady state of the solution. You're not oscillating. You are forcing something that has a natural frequency of 3 with a forcing of 2. This is standing behind a child's swing and pushing it with a certain frequency. Let's play with this model for different amplitudes and frequencies. And I'll leave you to play with this for a few minutes because we're at the end of the lecture. I want you to investigate how these things are depending upon the steady state of the systems. You can play with these sliders and look at how the steady state amplitude, as in that line right there, depends upon the forcing frequency, and investigate what happens when this gets close to the natural frequency of the system of 3. So play around, take a look, and the answer that we want to talk about, and we'll talk about this next time, is resonance all the way through. So we're at the end of the lecture, so I want you to play around with that, but before anyone disappears in case they have to go somewhere, this material is all reproduced and covered in the textbook, sections 4.2, 4.3, and 4.4, I think. 4? I'll have to check that. Whatever the chapter is on external forces. I've just rewritten the code for Python, not in Java. And it also completes the first unit that I wanted to cover in this course, which was the introduction to solving 1 and 2D dynamics problems using solving Newton's equations, basically, for oscillatory and particle motion. So one of the things we get to look forward to in 7 days from now is we've got a test. Yay! I know, tests, whatever. So I scheduled this for next Tuesday. Part of the reason I scheduled it for next Tuesday is I'm back in town. You'll get to see me in the classroom this Thursday. Please come to class on Thursday. I'm not sure I'll be able to record the lecture if I'm physically there. We'll talk a little bit more about oscillatory systems. But the test I want to give you on next Tuesday in this time slot is based on the material we've covered up till now. So if you want to study for this, prepare for this, look at it, it's lectures 1 through 8. Assignments 1 through 3 are going to be useful, but mostly 1 to 2. Just to give you a hint, don't worry too much about assignment number 3. Most of it will be on 1 and 2. And the labs that you've done for the last 2 weeks, and the one we'll do this afternoon, which is one on pendulums and such. Definitely study these different numerical methods, being able to talk about Euler versus Euler-Kromer versus Euler-Richardson, be able to understand this pattern that I have here on steppers versus plotters versus apps. Because what I'm going to get you to do is something equivalent to what we've done in the lab, which is give you some fill in the blanks type things and ask you to fill in the blanks. Now, this is where we need to have potentially a bit of a conversation. I've taught this course a couple ways, and I've played with having online exams where I give you a Jupyter notebook, like the lab, and I say, go to it, that's your test. There are risks in that. There are risks of things breaking and things not functioning. I'm sort of concerned about that. When I've done the online testing, I've made an open book and said, go ahead, use whatever resource you want. And what inevitably happens, so I'll explain my concern with it, is the people writing the test, you, the students, get caught up in something not working and are not able to demonstrate the knowledge that you actually have. So what I'd like to do for this test is not make it an online test. Make it a traditional pen and paper sort of test. And that means you're writing code in a fill-in-the-blanks type style. One of the things I know is going to be of concern is, well, there's so much to know. How am I going to learn it all? So let's come up with some ground rules here. I'd sure like you to be able to know this stuff and be able to reproduce it. I don't want you flipping through 8 labs worth of stuff or 8 lectures worth of material trying to find it. So what's sort of the norm about things to do here? Does that make sense in terms of a resource? Is that sort of a typical type thing you've done before where you're allowed to bring in a 8.5 by 11 sheet of paper? And I don't care if you use the front and the back. I don't care if you, I'm not saying it's a good idea if you use some font to go through things. Is that a reasonable accommodation for allowing you to take all the information? And because I'm going to ask you about Euler Chroma versus Euler, you can make a note of it. I'm going to ask you to fill in the blanks on some plot. I'm going to ask you something about time steps. I'm going to ask you something about writing a two differential equations or one differential equation in terms of 2 first-order differential equations. And I think pen and paper is the easiest way of not getting caught up in the details. So that's what I can say right now for it. I'm still drawing up my ideas on what I'm going to put on this thing. But that's what I'm thinking. We'll run it in the lecture slot. An hour 15 minutes would be the time. It's closed book. That means that please prepare that aid over the next week, or shrink things down, or however you like to study all the way through. But I think that's the best way of assessing people in this course. Any comments or questions about how that test might go? Again, I'm back in town as of this Thursday, so in the lecture, after the lecture, is there anything about the material we've covered to date you wanna go over? I'm happy to do that. I'll be around all Thursday afternoon, all of Friday, probably all of Monday, if that's useful, and we'll do a test on Tuesday. I've got the 3rd assignment due on Sunday, but there's no assignment due next week. There's no, well, next week being the week after the current week. There's no lab next week, so go through. Question, can you give us an outline on the format of the test? I will give you an outline for the format of the test. That's code for I'm still writing it. It doesn't exist yet. But let's talk about that on Thursday in terms of what to expect. My guess is at this point, you're looking at 3 questions that do the topics. It'll be breaking into subparts, and it'll have the same structure or format as a lab where there are blanks, and I want you to fill in the blanks, or short answer, explain why the times, what about this graph tells you the time step is wrong? Why did this code work? Circle the bug, find the mistake. Here's the output it gave. I don't know, things like that. But I will come up with some sort of outline document on Thursday for you, and we can definitely talk in person if that's useful. Okay, so we're at the end of the lecture period, which is really great, and we'll continue on in person next time. And we'll break now for the lab that I've got set up.